Hello everyone, and welcome to the Mat 211 review on partial derivatives. My name is Julia, and I work for the tutoring centers at ASU. So for today's problem, we're going to be looking at this function f of x, y, z equals 3 over x squared plus y squared plus z squared. We're going to take the three partial derivatives of this function with respect to x, y, and z. So the three separate partial derivatives. And then we're going to evaluate each of these at the point 0, -1, and 1. So first things first, let's rewrite this function so that it's in a little bit nicer form for taking derivatives. This part isn't technically necessary, but it will make your life a lot easier. So instead, we're going to bring up this denominator here as a negative exponent term. So what that means is, and we'll just write it up here in the corner to get it out of our way. So we're going to have f of x, y, z equals 3 times the quantity x squared plus y squared plus z squared to the -1 power. So that this guy here is equivalent to this guy here. So next, let's start by taking our partial derivatives. We'll start with the partial derivative of f with respect to x. So just like when we have just a f of x and y function, we're going to do this exactly the same, where we're going to look at whatever variable we're trying to take the partial derivative of, and we're going to hold the other two variables constant. We're going to treat them as if they are constants. So we have the partial of f of x, or f with respect to x, which we can say is the partial with respect to x of our function 3 times quantity x squared plus y squared plus z squared to the -1st power. So first things first, notice that this is going to require the chain rule, this part of the term here, because we have a full function, with an exponent attached to it, but then we have a nested function inside of it. So we're going to have to evaluate this with the chain rule. And we'll write this out explicitly so that it's not too confusing. So let's start by evaluating this 3 here. Since it's a multiplied constant 3, we just have 3 times, we're going to evaluate the outer part of the chain first. So that would be, we'll bring our -1 exponent down, -1 times x squared plus y squared plus z squared to the -2nd power, because we always subtract 1. Now that's all going to be times the partial derivative with respect to x of this interior function here. So x squared plus y squared plus z squared. Now recall that since we're taking the partial derivative with respect to x, we're going to ignore terms, we're going to treat terms that are in terms of y and or x as constants. So in this case, because these two terms don't have any x's in them, these are just going to go to 0. So we're only going to be looking at this term. So we have -3, we'll just combine those two, x squared plus y squared plus z squared to the -2nd power times our derivative here, which is just 2x for our x squared term, plus 0 plus 0. So we just have a 2x here. So we can combine these a little. We'll just bring this part over to the left side. We'll say -6x times our x squared plus y squared plus z squared to the -2nd. And now if we want to go back to writing this in fractional form, we can just say negative, and we'll have a 6x on the top, and we'll have our x squared plus y squared plus z squared to the 2nd power on the bottom. So whenever you move this back to the bottom, you just remove that negative from it. So there we go. We have our derivative with respect to x, or a partial derivative with respect to x. So now let's go ahead, before we move on to the partial with respect to y, let's go ahead and evaluate this at our 0, -1, 1 point. So we'll move over here. We say partial of f with respect to x evaluated at 0, -1, and 1. And as always, we're just going to substitute our 0 in for our x value, our -1 in for our y value, and our 1 in for our z value. So we'll have -6 times 0, because that's an x, and then that'll all be over. We have x squared, so 0 squared, plus y squared, so -1 squared, plus z squared, which is 1 squared, and that whole thing is going to be squared. So on the top, we know we have a 0 here. -6 times 0 is 0. And on the bottom, we'll have 0 plus -1 squared is 1. So 0 here. This is going to be a 1. And this is going to be a 1 squared, which is just 1. So it'll just be 1 plus 1. So we'll have 2 squared. Don't forget this guy. So this just equals 0. There we go. So we've taken care of our first partial derivative. So now let's clear the screen here, and we'll go ahead and take care of our partial with respect to y. I'm just going to erase, erase, erase. Takes a moment here. Erase, erase, erase. And so it's going to be much the same process for our partial with respect to y. We'll start with writing it out just to be nice and consistent here. So that's going to be the partial with respect to y of our function, which again, we'll use this form. So let's make these brackets here just to make it nice looking. So we've got 3 times our x squared plus y squared plus z squared to the -1st power. And it'll be the same thing as before. This is going to be a chain rule again for exactly the same reason. That we have an exterior function, our -1 exponent, and an interior function, this x squared plus y squared plus z squared. So again, we're going to say 3 is our constant and it's multiplied, so it comes along for the ride. And then we're going to take care of the outer part of the chain here. So that's -1, bringing down our exponent here. And then we have x squared plus y squared plus z squared to the -2nd, because remember, we're always subtracting a power every time we take the derivative. And then we're going to have that times the partial with respect to y of x squared plus y squared plus z squared. In this case, since we're taking the partial with respect to y, this guy is going to be treated as a constant, and this guy is going to be treated as a constant too. So these will both go to 0, and we'll only be evaluating the derivative of our y squared term. So that gives us -3, x squared plus y squared plus z squared to the -2nd power times the derivative of y squared, which is 2y. And we can go ahead and write this out. And we'll go ahead and move it right to fractional form here. We're going to have -6y. So the -3 times our 2y. And since this is going to be the bottom part of the fraction, this negative squared term, we'll have on the bottom x squared plus y squared plus z squared squared. So there we go. We have our second partial derivative of f with respect to y. So again, we're just going to go evaluate this at our point 0, 1, 0, negative 1, and 1 by substituting in the values for each. So we have partial of f with respect to y evaluated at 0, negative 1, 1 equals negative 6. Well, let's bring that negative up to the top just to make it nice looking. Make it a little less confusing. So negative 6. And then we have y. Y is a negative 1. So negative 1 over. Again, we'll have actually the same exact bottom as the first time, because you'll notice that this is the same denominator as we had in our partial with respect to x. So we're going to have 0 squared plus negative 1 squared plus 1 squared, and that whole thing squared. So negative 6 times negative 1, we've got a 6 on the top. And we saw before that the bottom is 2 squared. That's 2. And so this equals 6 over 4. And we can reduce this to being 3 over 2. So there we go. That's our answer for our partial with respect to y evaluated at our point 0, negative 1, 1. So let's go ahead and clean up again a little bit here. And we'll do our last partial derivative. All right, erase, erase, erase. There we go. So we're doing the partial of f with respect to z. And we'll write this out again. Partial with respect to z of three times x squared plus y squared plus z squared to our negative 1 exponent. There we go. It's the same process as before. We'll have the same chain rule issue as before. So we have 3 times negative 1. So we're going to, again, evaluate the exterior first. Times x squared plus y squared plus z squared to the negative 2nd power. Times our partial derivative of the interior with respect to z. And that's going to be, so again, x squared, that doesn't have anything to do with z, so that's going to go to 0. Y squared doesn't have anything to do with z, so that's going to go to 0. And so we'll just be evaluating our partial with respect to z squared, or partial with respect to z of z squared. So that would be 2z. So we can gather our terms here. And we have, again, negative 6, in this case z, times our x squared plus y squared plus z squared, the negative 2nd power. And so, again, in fractional form, we have 6z over x squared plus y squared plus z squared squared. So that is our partial derivative of our function f with respect to z. All right. And lastly, we just need to evaluate this at our point. It's going to be the same process as before. We have partial of f with respect to z evaluated at 0, negative 1, and 1. And that'll give us, we'll put the negative 6 on top here, times z, which is 1, all over. And this is going to be the same exact denominator as before, but let's write it out just to be clear. 0 squared plus negative 1 squared plus 1 squared squared And so we know this bottom denominator evaluates to 4. And we have a -6 on the top, so -6 plus or times 1. So that gives us -3/2 for our final value. It is important to note that you won't always have, the same denominator in all of these cases. This just happens to be the case because we have this special situation where we have an x squared plus a y squared plus a z squared. So it has this nice symmetry to it. But that won't always be the case. So always definitely check each time to make sure that that is the case. So that's it for our problem. We've solved everything we needed to. So I'm going to clear these drawings and move to the next page. So before I go, I just wanted to remind everyone that if you are looking for any additional tutoring services or academic support at ASU, you can go to tutoring.asu.edu. You can also use the tutor search function or tool, which can be found at this full link here, or just right on the main page, tutoring.asu.edu. And this will allow you to find tutoring services for a specific course. So thank you so much and have a great rest of your day.